Hi, this is Jeff from the Ozark Mountains in Missouri, USA. You might be thinking, hey Birt, what's the deal? Are you lost? Well, the story goes something like this. A few weeks ago, Robin from the 8-Bit Show and Tell channel talked about some of the Commodore BASIC shortcuts he's grown accustomed to using over the years. By happenstance, I happened to read a blurb about that in an old issue of the Transactor, where it mentioned that it was an accident. It was kind of a side effect of how the BASIC interpreter worked, or the parser, but it didn't really go into much detail. So I asked Robin if he knew why that happened to work, and he'd heard similar stories to what I did, but had never seen an explanation as to why. I attempted to look into it, and I found a few things. A web page here where it mentions that in the 6502 BASIC, there were some new things, including line crunching, which required program lines to not have any spaces between the line number and statement. Another tidbit I found here mentioned something about the abbreviations having something to do with the high bit of the letter being set. And I was happy to find that the annotated source code for the Microsoft 6502 BASIC was available online, and it's really well documented here. So, Robin, do you think you could look into this and explain to the rest of us how this basic shortcuts for the basic abbreviations happen to work? It's amazing to me that, nearly 40 years after Bill Gates wrote the 6502 BASIC, we're still finding out things about it and are still, fascinated with a few K worth of source code.
Thanks for the question, Jeff. It's been about a month since you first asked me about doing this, and I've been reading up about this subject ever since. In fact, just a couple days ago, I tried recording this and got stumped on a problem, so I stopped and made that little video about Neutron, the shooter, and I thought I'd come back to this again tonight. Jeff actually did a bit of research about this subject, and he suggested I look at Transactor Magazine, Volume 5, Issue 2, and as soon as I pulled it out of my collection, I have all the Transactor magazines, I realized that this is the very first issue of Transactor I bought way back, I think it was August 1984. I would have still been 11 years old, and here I am, going to the corner store and buying The Transition to Machine Language. And this magazine, I think this changed my life. Reading these technical articles, if you don't know about Transactor, it's a Canadian magazine. I think that explains why it was one of the very few available in my city. It has some close connections with TPUG, which included the famous Jim Butterfield. He was a regular contributor to this magazine. Every issue had pretty cool art like this. This issue actually has 2 articles about the subject, all about Commodore BASIC abbreviations by Louis Sander, and you might recognize his name as he went on to write for Compute Magazine and some books I believe I have in my collection. And a couple pages later, this article, How BASIC Works, which includes a description of the crunch routine that tokenizes BASIC, which is the cause of these BASIC abbreviations. So on the previous page, there's this editor's note about how the abbreviations phenomena is actually the result of a bug. A quite harmless bug, but a bug just the same. So, what are some abbreviations? You probably know the extremely common one. You just use the question mark, even just by itself. And if you list that, you see how the question mark is being expanded out to the full word print. Now, just the list itself can be abbreviated with L-Shift-I. The question mark for print is a special abbreviation. It's actually the only one in Commodore BASIC that gets a single symbol. I think it's because print is such a commonly used keyword. All the other abbreviations require you to type 1 or 2 letters and then followed by a shifted character. So it's actually easier to see what's going on if we shift to lowercase. You can see this is L-Shift-I. Some other common ones, instead of typing in load, you can type in L-Shift-O, and you see it tries to load from tape. Or the frequent poke can be abbreviated to P-Shift-O, 53280, 0, for example, to change the border to black. Now, abbreviations work equally well whether you're typing them in direct mode, so they execute right away, or if you put a line number in front then it gets stored as a line of basic code. Either way, the abbreviations work. Now notice that Commodore BASIC doesn't actually do any error checking when it's crunching the line that you've entered. For example, if we did 10 and then do a whole bunch of question marks and press return. Now, if we list that, each of those question marks has become a print statement. But if we try running that, then we get the syntax error. So crunching a line, or I'm calling it crunch, but basically it's whenever you press return, BASIC parses that line partially, not to execute it, but to convert any keywords into their tokens. Tokens are a single byte representation. Now the token, it doesn't actually get turned into 5 characters, it gets turned into a single byte with the high bit set. We'll get into that more later. Now some more unusual abbreviations include P, Shift, R. I'll go back to lowercase so it's easier to see. I, Shift, N. You can probably guess what some of these are. R, Shift, I, T, Shift, A, and G, Shift, O. Okay, we'll list that. Each one of these is being converted into its keyword. So notice that P, Shift, R doesn't give you print. Instead, it gives you print number sign, which is a separate command to print to a file. I, Shift, N brings up input. Again, a special version of input with the number sign attached to it, which is for inputting from a file. R, Shift, I is the write string command and includes that $sign to show that it's a string function, but it doesn't include the opening parenthesis. But notice how T, Shift, A is the tab function, which I mentioned in previous episodes surprised me. I used to think tab was a string function, but notice it doesn't have a $sign, and strangely it includes the opening bracket. Tab and the SPC, space function, don't actually return strings. They're only used within print commands. I discussed that in a previous episode. So it's interesting to note that these are the only 2 keywords with the opening bracket built into them. And G, Shift, O is the goto command. So that's some examples of abbreviations, but there's still a lot deeper that we can go. By the way, on all my episodes lately, I've been making up an index, which I post in the description below and also pin as a comment. So if you think I'm being long-winded or you just want to skip to the next part, go look up that index and go ahead and jump to whatever interests you, if any of it does. Now, what's interesting about input is that there is no abbreviation for a regular input. Because if you try, here we'll try I, Shift, N. Well, we already did that, didn't we? Okay, that's input number. Now if you go I, N, and Shift, P, that also has the number sign attached. And here's something interesting. You can actually shift following letters and still get it to pick up on the abbreviation. So input with a Shift U, and we'll list that. That is also the input number sign. Okay, so we'll go a little bit deeper here. As usual, I have my Super Snapshot cartridge plugged into the back of the computer here, and we're going to use the monitor to look at this. So let's just do a new line of BASIC, line 1. Doesn't matter what line number you do. And I'll just type a print. Okay, so we've entered that in memory. Now I'm going to use my freezer button and M to go into the monitor. And there is a buffer where any command, whether it's an immediate mode or a program line, it gets dropped into memory here. And this is the buffer after it's being processed. The line number has been stripped off. Actually, let's look at it in memory. Okay, this is where the basic code has been stored. So at location 0801, the first 2 bytes actually point to the memory location of the next line of BASIC. So this is in low byte, high byte. So this is 0807. So it's actually pointing here to these zeros, and all BASIC programs end with 3 zeros in a row. So that's here, 1, 2, and 3. Okay, so that's the first pair of bytes. The second pair is the line number in integer format, again, low byte, high byte. So this is line number 1. So this is 1, and the high byte is 0, as you might expect. And then there's a 99. Well, 99 is the token for the keyword print. And I'll show you more about that in a bit. And then every line of BASIC ends with a 0. I actually have here the Complete Commodore Inner Space Anthology by my friend, Karl Hildon. Actually, he signed it for me there. I met Karl about 15 years ago. I was in Toronto just after the release of the C64 TV that I worked on with Jerry Ellsworth and other friends. We were down in Toronto for T-Pug's anniversary, 25th anniversary. Yeah, maybe they started in 1979. Anyway, we were there in 2004. The C64 TV had just got released. And there was a group of guys standing around. And one of them was Jim Butterfield, who is, of course, famous to us, especially here in Ontario, where we watched him on TV every week for years as they replayed the TV show Bits and Bytes and the Academy over and over again with Jim Butterfield. But there's another guy there. So I walked up and I said hi to Jim because I had met him before. And then I got introduced to Karl Hildon. I had never met him before. And Karl Hildon from Transactor, I said. And he goes, yeah. And I was like, whoa. And I totally, it was a fanboy moment. Anyway, Karl and I became friends. And for a number of years thereafter, when I'd end up in Toronto, I even drove me down to the Personal Computer Museum before Sid Bolton died. Anyway, that's a big diversion. This is an amazing reference. And you can probably find it online somewhere. But here on page 37 are these things called the SuperChart for the VIC-20 and Commodore 64. And you have a listing of decimal, hex, and then ASCII values, and then the screen codes, and then BASIC, then 6502 as an opcode. So this is an amazing reference. It's kind of when you're doing a disassembly of something, you just have a number on the screen. This allows you to see the context. Like, if you know the context, then you can figure out what it means. And here in BASIC, if we look up hex 99, that is the token for print. There you go. So every keyword that you type into BASIC, no matter if it represents a 2-letter or a 5 or 6-letter keyword, gets crunched down to a single token, almost as if it's an opcode at the BASIC level. And this allows BASIC to actually, this is one thing that BASIC does well, it's a good optimization for BASIC. So this is how it looks when it's in BASIC memory at location 0801. But here's where it's being crunched in the line buffer at 200. It simply is being turned into 99, that's the print opcode. The line numbers have been stripped away, and then a 0 to show it's the end of the program line. And this is actually garbage left over from other things we've been talking about, like when I was typing in those inputs. But the 0 is the null, the terminator. So that's it. So that's one example. So we'll resume here. Now, just to illustrate that a bit better, we can do 3 prints in a row. Okay, and for example, here's the data keyword, which is hex 83. So I'm going to just stick a data on the end, just because. D-Shift-A will list that. Oh, no, we won't. I want to show it in memory, so I'm going to, if I typed in another command, that would actually overwrite the one-line buffer. So we're going to look at 200, and here it is. 99, that's the first print. 3A is a colon. 99, 3A, 99, 3A. And there's 83, that's the keyword for data. Then there's a 0. Okay, so you see how that works? Whatever commands you type in get crunched down. Actually, one more just so you can see how this works. For example, print, or if we type print, and if we do a poke, 53280, 0. Okay, let's take a look at that. Okay, so there's our first print, colon. There's our second print. See, even though I typed in print in full, and here it was with a question mark, either way it gets turned into that 99 token. And so I think some people think if you use those abbreviations, it'll actually speed up basic execution, but you can see here that that's wrong. The only real advantage to using the abbreviations, you can save keystrokes. It also allows you to cram a bit more into a line of BASIC, which is usually limited to 80 characters on the C64, and actually lets you get more characters crammed in a line, but then there's problems editing it after. I think I got into that in a previous episode. Okay, and there's the colon. And now, here interestingly, 97 is the keyword for poke. And then you can see over at the right here, these are actually ASCII 532. And then you can see here that this is all PETSCII 53280, 0. And then there's a 0 at the end, 0 hex, to signify the end of the line. But constants like 53280 and then the 0 at the end of the line are just stored as PETSCII, and they have to get parsed every single time you run them. In that previous basic optimizations episode, I got into that, how it's actually quicker to just store those kind of constants in a variable rather than having them parsed out each time. Okay, so you get that idea. Now, while we're in here, we're going to disassemble at 1000. And we've looked at this in a previous episode when we were looking at all the various error messages. But here's what I want to show you. And if I shift to lowercase again, it makes this easier to read. So up here, this is a table containing all of the basic keywords. EN and Shift D, FO, Shift R, next, and you see that at the end of each keyword, the last letter is shifted. Really, it's the high bit is set. If we look over here, 444154C1, this larger number, these are both A's, 41 and C1. This is a lowercase a when we're in this character set. And the C1 is the same value plus 80 hex, or 128 decimal. And here's input spelled in full, and then this funny symbol. Well, that is the number symbol with the high bit set. And afterwards is input with the T shifted. Now, this is the cause I mentioned before, how input without a number sign, the regular input, does not have an abbreviation. This is why. When Commodore BASIC is tokenizing, it's going through and reading what you've typed in the buffer and try to match that to one of these keywords. If it finds a match, when you use an abbreviation, it actually matches with the input number sign first and never gets a chance to match with the shorter string. I'm not sure why they did it this way. If they had reordered it so the shorter input was first and then the longer one afterwards, then the regular input would have been abbreviatable. Is that a word? And it goes on. There's dim, read, let, go to, run, and so on. gosuB. Now I'm going to show you the abbreviation that totally stumped me when I tried to record this last time. I just quit recording because I was so, I don't know, I just had no idea what was going on here. If we do the gosuB command, I'm going to type 3 letters and then shift the U and then list it. You see how it still turns into gosuB. Okay, but if I do gosuB and then I shift the last letter, this was the craziest thing. I tried this, and then you list it, What? Bizarre. So this was enough for me to just quit recording the other night. I think I mostly figured it out now. Why would gosuB get turned into this mess? Okay, well, I think it's two things are happening here. We can see the parser generally throws out shifted letters unless they are inside a remark or quotes. So I think we can ignore that one. I could prove that later. But now you see what kind of the match is here. The SU and SU matches up, and the go becomes the mid-string. Okay, now why would that happen? Well, a lot of people don't know that if you got your regular go to command, right? But did you know that go to with a space in between is a legitimate keyword? It actually uses a different token. Here, we're going to list this. See how that space is preserved? So if we go back to the SuperChart here, you see how there's the go keyword here on its own. Well, what's the one right before it? It just so happens to be mid-string. So what's happening, I think, is that the go is getting interpreted, but then the counter is never incremented. Basically, as the tokenizer is going through all these different keywords one by one, and it hits mid and does not get a match, it hits go, but it actually doesn't get the counter incremented, so it's still pointed at mid-string, and then that's what gets entered in. Okay, I'm fairly sure of this, but I spent quite a while looking through the disassembly. It was not fun. So I think that's what's going on here. If anybody wants to exactly explain it, be my guest. Okay, and to go a little bit deeper with this, I'm going to go back into the monitor. And a problem we're having is that we're only able to look at the buffer once it's being crunched. But the fact is that actually the original line is put in the buffer and then it's crunched in place. They didn't use a second buffer, but the existing line is actually crunched over top. And because the line is guaranteed to get shorter as it's crunched or tokenized, they actually reuse that memory in the location 200. So what would be great is if we could take a look at the buffer after we hit enter and it's copied, but before it gets crunched, and it just so happens we can. If we look at memory at location 302, here there's a number of vectors. Now actually it's because I have the Super Snapshot cartridge installed, it's actually a weird address here, DEFA, which is actually IO space. It's actually pointing to a small machine language routine within the Super Snapshot cartridge, and this is part of how they intercept the regular operation of the computer. Normally this would point to location A483, but because the Super Snapshot's installed, it's pointed to DEFA, and then the second 2 bytes are normal, point to A57C, which is part of BASIC. Okay, and these are both called vectors, which are 16-bit addresses within C64 memory as part of the kernel and BASIC operating system. You can actually intercept these, and it's a very powerful and flexible part of Commodore BASIC. Despite all its shortcomings, it's got some neat tricks in it. Here in programming the Commodore 64, it's got an excellent description of these vectors. So we're going to be changing the vector for location 302, iMain, the vector to the main BASIC loop. Usually it points to A483 as called just after the ready prompt prints. So that's handy because we can see what BASIC has done before it prints ready. And even more useful is location 304 here, iCrunch, vector to tokenize keyword routine, and you can actually jump right in there. Okay, so that's what we're going to do. So it's very simple. We just point this vector to location C1000, C000, and this one to 04C0. I press return. And so we're just going to write a small routine now that we've changed the vectors. I assemble at location C1000, BRK, and that is a break opcode. It's like a interrupt, but software controlled through an opcode. And if you're a programmer on more modern machines, I'm sure you've heard of breakpoints. Well, this is part of where that originated. This is like well, not the original breakpoint, but going back into the 1970s, this is how breakpoints were done, with actual break opcodes. And it just happens to be opcode 0. So if memory is initialized with 0 at the beginning, then you will likely hit one of these, and it's useful for debugging because it causes the CPU to do a interrupt that you can intercept. Okay, and then we're going to jump to the regular routine that handles the ready prompt. And then we're going to do another break. And we're going to jump to the regular routine, A57C, that tokenizes BASIC. Okay, so all we're doing is, it's just the regular execution, but it's going to call a break interrupt along the way so we can easily intercept and like just look at memory and then continue on. And the last thing we have to do is, for the Super Snapshot monitor, the BR command is what intercepts the break interrupt vector so that our routines will be called. Okay, so one example here, we'll do question mark, colon, and then print rem high. Okay, I just hit return, and now it's interrupted. We can look at memory. So here we should be able to see it here in the buffer. Yeah, if you look over on the right here, there's the line number. So this is just the plain text of what we just entered. Question mark, the full command print, the rem command high, and then it's null terminated. It's got a 0 right here at the end of the string. So we can see how that's being entered. And now we just press G to continue on, to go. It'll just default to what the program counter is here, which is just the jump back to the regular operation. Okay, and now it's interrupted again just before it prints the ready prompt. And now we can look at memory at location 200 and see it's being tokenized. Now all that got turned into 2 prints, both 99s. And then the 8F is the rem statement, a space, HI for high. And now the line has been terminated with a null pointer. You can see that some of the leftover text is still here, like here's part of the rem that we typed in and the high and so on. So it's being crunched down to this section. And then this is just, it doesn't bother to clean up after itself. Well, hit go, back to regular operation. Can even test this with like print high. And if I press return, that'll be in memory. Here it is, high with a 0 at the end. And we go, and then we can see that it's being crunched down to just 99, the quotation mark, HI, closing quotation mark, and the null. And if we hit go, it'll actually print the high out. So the computer's almost operating normally, except we can interrupt it at these key points to inspect what memory looks like. Okay, we'll go back into the monitor. And just because Jeff asked so nice, we'll take a look through a partial disassembly of how this all works. So the routine starts at A582. And you see here how we're loading a character from the buffer. Okay, and this is checking to see if the high bit is not set, then it branches ahead to look for spaces and variables. Otherwise, it compares with the character FF hex, which is actually pi. Strangely, it makes a special case just for pi here, And if it happens to be equal to that, then it jumps ahead to the stuff routine, which is A5C9, and we're going to be seeing that one a lot today. Okay, and otherwise, it's going to be increasing X to look at the next buffer, and it does a branch if not equal to 0. Well, it's always not going to be equal to 0 because it's an 8-bit counter. It's never going to reach that 256 characters because the line length isn't that long. So it's going to increase and look at the next character. And here you have routines looking for whether it's a space or not. If it is a space, that's what hex 20 is, then it's going to branch way ahead. We'll be here all day if I go into every detail. This is searching for hex 22, which is actually a quote, and the cruncher actually handles quotation mode separately. Here's where it looks for a question mark for the print command, and this is a special case that it's checking directly for the print command. If it's not, then it's going to branch ahead to here at A4, but if it is, there's that hex 99 for the print token, and off it goes to that A5C9, which is the stuff routine that we've already seen several times here today. Next, it's going to check for PETSCII 30, which is PETSCII for the 0 character, and branch carry clear, that's if it's less than, that's all that punctuation. 30 hex here is 0. You see all this punctuation here, that all comes before. So basically this is checking for digits 0 through 9. Oh, sorry, this doesn't go to 9. This also includes the colon and semicolon, which are right after them. And off it goes to A5C9. So it just stuffs any numbers, semicolons or colons. Okay, and so it's done reading the first set of characters. Now it's cleared all the other possibilities. Now it's going to start searching for keywords. So this is some setup here, and this right here, and this is the core loop that searches very efficiently for keywords. Y is the index into the keyword table, and X is the index into the buffer. This means look at character. If X is 0, then it's going to look at the beginning of the buffer. If X is 1, that X value gets added on. This is called indexing. So this is going to load a character in the buffer that's currently looking at. It's going to set up for subtraction, set the carry, and then it's going to actually subtract. A09E is that keyword table we were looking at a little while ago. So it's going to subtract. If the letter in the buffer matches a letter in the keyword, then it has a potential match here. So if it is equal, then it just simply branches back here to look at the next X and Y, which is the next character in the buffer. And so as long as there's a match, it'll keep looping. If it's not a match, then it checks for a difference of 80 hex, 128 decimal. If the difference is 80 hex, then it assumes it has a match between what's in the buffer and the keyword, and it's reached the end of that keyword. So if it's not equal, then it jumps ahead to start searching for the next keyword because it wasn't a match. But if it goes here, then it thinks it is a match. And so what it does is it ORs B, which is actually the index, the keyword counter. And because the accumulator must have 80 hex in it, essentially it's taking the keyword counter and adding 128 to it. All the tokens, did I say that already? All the basic tokens have their high bit set. That's what sets them apart from the regular PETSCII of the constants and so on that you might have. So now the accumulator has the matched token in it. Oh, and then it stores it. Actually, this is interesting that it doesn't store it at 200. It's offset by 5 characters, which is the number of bytes at the beginning of each line of BASIC. Okay, and so that stores the token in the buffer. It's now crunched. And it's storing it at the beginning. So like we saw, it all crunches to the left, so to speak. So just to examine this a little bit more, this is where it gets the character, subtracts the value of the character in the table If it's 0, it's a match to continue. But if it's off by 80 hex, a difference of 128, as if the high bit is set, this is why basic keyword abbreviations work, because the code does not bother to check whether the high bit being set is from the end of the keyword table, or if it's just because the user shifted one of those characters. It can come from either. And this is why when you shift the last character in your keyword, why it does not work. That's the origin of the bug. So potentially this could be rewritten to actually check if this value coming off of the table has its high bit set. So for example, I'm not sure we could squeeze this in this space that we have. Instead of loading from the buffer first, we load from A09E, and then we can check the high bit with the BMI branch if minus, meaning the high bit is set, and then do a bit of logic. The only thing is I couldn't figure out, I wanted to try and fix this bug, even though it's actually a pretty useful or handy or fun bug. But I couldn't figure out how to easily squeeze it in here, so anyway. If somebody can think of how to fix it without using any extra bytes, that'd be awesome. Hey Birt, that is what I know about keyword abbreviations. That was a lot of work, but it was also a lot of fun, and I hope my explanation helped. I'll leave a link below. Make sure you check out Hey Birt's channel and subscribe to him. He's a great guy with lots of interesting content on his channel. He gets into programming and also some hardware stuff. And thanks for watching. We'll talk to you next time.